Good day and hello. I'm very sorry that I cannot be in person in Ferrara this time because we have a meeting here in Ottawa. However, at least I hope that I can convey myself and the ideas in this talk via video. My talk is about brain and heart, and I'm sure you have seen in your practice, in your clinical practice, many patients, psychosomatic patients with sort of unspecific heart palpitations, heart pain, and you cannot find a proper explanation for that because they go through the cardiologist, no findings, and finally, after many investigations in internal medicine, they end up with you as a psychosomatic expert. Basically, everything that remains unknown in medicine is delegated to you. And I want to show in my talk a little bit, shed some light on that, and you see already here the title of my talk, Brain and Heart, a tango across cardiology and psychiatry. And as you know, a tango is always between two people. And the better the two people harmonize, the nicer and the more beautiful and the better the tango. And the same applies to brain and heart. So meaning, if they truly love each other, as you can see here, then the tango will be perfect. And you will not have symptoms. However, when the love is sort of problematic, then there might be some symptoms, and that's the moment where you come into play as a psychosomatist. Yeah, how are brain and heart connected? You sure remember that all from your medical school or from your education. There are various ways. The heartbeat is processed by the brain's activity. I will show more some data on that in the following. And on the other hand, you all know that the brain controls the heart and its activity, particularly through the autonomous nervous system. Sympathicus, parasympathicus. There are also other pathways, neuroendocrinological, neuroimmunological, which I will neglect here. Here, I already said, physiological connections, vascular, metabolic, endocrine, immunological mechanisms, but I neglect those for the sake of simplicity, in particular focus on certain temporal mechanism of how the activity of the heart over the time is related to the brain over the time. And this is what I'm doing here. So specifically, when you dance to music, you align your rhythm to the music, meaning your dance movements or your finger or movement or foot tapping is in tune, in line with the rhythm of the music. And the same exactly happens here. The brain aligns itself, its own rhythm, to the rhythm of the heart. And that is quite amazing. One can also speak sort of a temporal alignment of the brain to the heart rhythm. And that, of course, goes back to some synchronization between brain and heart. And I want to show you some examples of that later. The overview of my talk, first I want to provide very briefly clinical evidence of brain-heart connection in psychiatric and cardiac disorders. So I show you some shared symptoms. Second, I will show you some temporal spatial mechanism of brain-heart connection in the healthy state. And third, I will show you some abnormalities in brain-heart disorders on the neuronal side. So let me start with the first one, the clinical evidence. You all know depression, and you all know this, that there's a sort of focus, ruminations, focus on the own thoughts. And you also know that many of the patients, of the severely depressed patient, present with strong somatic symptoms. That concerns often the digestion, the appetite, but also very often the heart palpitations, unspecific heart pain. And I remember one patient who basically went 8 months through different cardiologists and they couldn't find anything. And finally she ended up in our department, and it was clear that she had a severe depression, a somatic depression, as we call lavierte Depression in Germany, and particular somatic depression. And you probably also know maybe some of the immigrants from people from Middle Eastern countries that they have a much stronger expression, somatic expression of the symptoms. And then I remember when I saw some of these patients at the beginning, and they said, oh, they said they have a heart attack. I was really concerned, but it was just some heart pain, and that's the way they expressed their depression. So depression is a typical example where you really have both psychic symptoms and somatic, in particular cardiac symptoms. Yeah, here, so you really have somatic cardiac symptoms. Yet another typical example, even better, are anxiety disorders. You probably all remember your first panic disorder patient who said, I have a heart attack, I have to die, and she or he comes into the emergency room, and the people with, and then the internal medical people come and assemble around and try to find a cause, and they can't find anything. They do EKG, they do echo, they do ultrasound, etc., can't find anything, and then they finally call the psychiatrist. And recently, very interesting, in my interaction with the cardiologist, they also told me that there's sort of a psychogenic heart attack. So they have all the symptoms of a heart attack. Apparently, they also have some EKG, typical EKG abnormalities. So they're basically doing angiography, and then they want to replace the stent. They want to insert a stent, basically resolve the blockade in the coronary artery. However, when they see the angio, there's nothing to resolve because there's no blockade in the coronary artery. So there is this suspicion that this might, and often this kind of sort of psychogenic heart attack occurs in highly anxious patients and almost always in response to specific life event. So meaning again, here you have a cardiac, you have psychogenic somatic symptoms. And here it's also very well known that in cardiac disorders on the other side, meaning in atrial fibrillation, a rhythm disorder, or a myocardial infarction, you have a higher incidence of comorbid anxiety and depression. So that is well known, has been well reported in coronary artery disease, myocardial infarct, also in myopathies. You have an increased incidence of comorbid anxiety depression. So it's basically really from both sides, brain disorders, psychiatric disorders, like anxiety disorders, like depression, show a high incidence of somatic cardiac symptoms, while on the other side, cardiac disorders, like atrial fibrillation, myocardial infarction, show high incidence of psychological symptoms like anxiety and depression. So that really shifts the focus to the second part of my talk. What are the neuronal temporal spatial mechanisms of brain-heart connection? So here I show you some data from our own studies. So you have a continuous rhythm of your heart. I don't need to tell you. You have an EKG, and this is, for instance, presented here. You can see this here. This is the heart. This is the EKG compressed. And then basically what you can do, you can try to analyze the dynamics, the variability of the heart rate. So this is called heart rate variability. And you use windows to see how much it changes over time. And on the other hand, you have in the brain, you have also a time series. So you can see here, this is a time series of activity of amplitude changes in the brain, particularly here in the motor area. And you can do exactly the same kind of analysis as in the heart beat time series. You can also analyze in 30-second windows. Yeah? And then you can test whether these changes in the amplitude in the brain are related to the changes in the amplitude of the heart. So basically you can test whether the heart rate variability, the changes in the amplitude of the heart rate over time, are related to the variability of the neuronal activity / its degree of change over time, from time point to time point. And that's exactly what you can see here. Here I showed you a typical example of where it really goes in synchronization, the changes of heart and brain amplitude activity. You can see, for instance, here, this is the bold, this is fMRI. This is a variability amplitude change of the signal in fMRI, which is called bold. And SD stands here for standard deviation, meaning the amplitude change over time. And what you can see, and here we have the amplitude change of the heart rate variability, slash the SD of HRV, heart rate variability, standard deviation. And we analyze that with sort of over time, and you can see, for instance, very nicely here in red, you can see here changes in the heart, changes in the brain, changes in the heart, changes in the brain, and somewhat. So there seems to be some kind of alignment. It's like, as I said initially, when you hear music, you unconsciously tap your foot in the rhythm of the music, and that apparently seems to occur between heart and brain too. And this is a particular region here called the ventromedial prefrontal cortex here in the anterior part of your brain. Interestingly, that region does not only mediate apparently the heart-brain synchronization, but also, that is well known, our sense of self. So here we have yet another region where you probably would say this is more likely is in the midbrain, where you have a lot of autonomous nervous system parts. And you can see again somewhat synchronization between the brain beat and the heartbeat, if you want to say so. So the fluctuations in the amplitude over time seem to be somewhat synchronized in different regions of the brain with the heart. Then what is important, as you may know, so you have fluctuations in the heart rate activity, and these fluctuations, these changes occur in different frequencies. They can occur fast or slow. For instance, go to the Mediterranean Sea. I know it's not far from here in Ferrara. And you will see, you feel slower waves and faster waves. And fast waves occur obviously often, and they're very, very small. Bigger waves are more powerful, occur less often. And the bigger waves are usually slower waves. They develop over time, and they take some time, and then also to rise and then to play out. Whereas the faster waves rise fast and disappear fast. And the same thing is in the heart rate changes. You have changes in different frequencies. Yeah? So in different speed, you have the changes, and one can distinguish in the heart rate but different degrees of frequencies. And that is important, is in a frequency range, which we say between 10 seconds and 1 second. So that's sort of the frequency range of the changes in the heartbeat amplitude. Yeah? So you have 1 to 10 second sort of, in that range, you have different kinds of change in the amplitude of the heart rate. Interestingly, you have a somewhat similar frequency range in the brain, which is a little lower, which we can measure with fMRI. And here you can see this is what we call the power spectrum. You can see again a lot of power in the slow waves and less power in the faster waves. So just like it's a Mediterranean Sea, you're not afraid of the small waves because you can just, they don't smash you down. However, when a really big wave comes, then you're really afraid, and you should be careful not to get lost in the sea. And the same in the brain. You see a lot of power in the slow waves and less power in the faster waves. And ultimately the same holds in the heart too. So you have similarity in your frequency changes. So that means that sort of brain and heart can synchronize each other in their respective changes. So my change in the brain activity is somewhat related to the change in the heart rate activity. Same when you dance a tango. When your partner changes the position of her or his legs, then you will also change the position of your legs, and vice versa. And the better you can synchronize the change in the position of your legs with each other, the more you might be in tune with the music, the more you might be in tune with each other, and the more better you might align to the music. So same here, brain and heart seem to really alignment with the mutual coordination of the temporal course of neuronal and cardiac activities. So it's really a synchronization. That's what I hear. Neural and cardiac activity share the same rhythm at specific points and probably also over time. And importantly, that can occur in milliseconds. That's what I want to show you now. So here we plotted, this is an EEG study or an MEG, magnetoencephalography, and that allows really a millisecond precision of neuronal activity. So what we did here, we took the R wave of the heart rate of the EKG and plotted the time onset of the heart rate of the R wave of the EKG exactly to the neuronal activity change. And when you average across different heartbeats, R waves from the EKG, then you can see what we call a potential, a heartbeat-evoked potential. This is what you can see here. At 0 is basically your R wave, and then you can see some change here in neuronal activity, specifically related to the R wave. And you can see there's a fluctuation here, and then it goes high, and this is the timing. So meaning how the heartbeat the R wave is processed in the brain and how it wanders from different regions. So you can see at 0 millisecond at heartbeat onset, it's really here in the somatosensory cortex. And then it moves what we call the insula at 250 milliseconds. And then it goes to the ventral medial prefrontal cortex here at 400 milliseconds. And you can see these are electrical changes. And here the 3 colors are the 3 different regions, the somatosensory cortex, the ventral medial, and the insula. And you can see also in the curves they're somewhat different. And you can see the locations here. So meaning the heartbeat is sort of processed by the brain. It sort of wanders through the brain. It leaves its impact everywhere in different regions of the brain. And all these regions basically try to align or synchronize with the timing of the wandering heartbeat. So that has been shown. And here you can see it even stronger. Here you can see basically the degree of synchrony which heartbeat and neuronal activity achieve. So we call this intertrial coherence. It's basically that the brain locks or phase locks its activity to the onset of the R wave. You can see again the R wave from the EKG here. And you can see increased activity just around the R wave, exactly time locked. And this is just 500 milliseconds, so it's very short. And you can see there's increased activity. So meaning here, we can really show that the brain locks its activity to the R wave of the EKG. So meaning the brain goes with the rhythm of the EKG and your heart. In the same way you follow the music when you tap your foot. In the same way the brain follows the beat of the heartbeat. That you can see, and you can see it in specific regions of the brain. Here's the insula, somatosensory cortex, and the ventral medial prefrontal cortex. So you see there's absolutely timing precision. So meaning you have more long-term mechanism. Remember the neuronal changes over time, what I showed you in fMRI. And we have also more short-term. This is basically the synchronization at one particular point on time, here by the heartbeat evoked potential or the intertrial coherence. So now, of course, the question is, maybe some of these mechanisms are altered in patients who have depression and anxiety, as well as somatocardiac symptoms. So I come to the third part of my talk, to the abnormalities in brain-heart disorders. So here, what has been shown in anxiety disorders, here I show you that even our sense of self, let's say our emotional self or the mental self or the bodily self, is related to different networks. And like the default mode network, this is in the middle of the brain, somatomotor network mediates your movement, and salience network, you can see here the regions, mediates emotion. And what is important that all these 3 networks have been shown to be strongly coupled to the heartbeat. So these regions, these networks, synchronize their activity in the brain with the activity of the heartbeat, of the heart rate. So basically you can clearly see, and psychologically they mediate a sense of sort of a mental self, this network, or I am aware of my own body, bodily awareness, and emotion in the salience network. So you can see that all these three features, emotion, bodily awareness, sense of self, are based on specific networks in the brain, which in turn are strongly synchronized with the body. So literally these psychic functions are closely based not only on the brain, but also on how the brain connects with the body. And now you probably see, you are all experienced clinician, that you see that exactly these kind of symptoms, that they're altered in your patients. So here, for instance, in anxiety disorders, it is well known that the default mode network activity is decreased. So, and it is also known that in these patients, the heart rate variability, the change, is decreased. So we now assume that this decrease in this network in the brain might be related to the decrease in heart rate variability, and then that you sort of lose your sense of self. That also you all know that these patients have extremely strong awareness of their own body, not only of their heart and heartbeat palpitations, but overall, and that might be related to this network, to the somatomotor network, and then also to its abnormal or decreased coupling with the heartbeat. Finally, you know that in particular social anxiety, you have extremely strong anxiety or fear, which is related to the salience network, and which again is strongly rooted in the coupling, in its coupling and synchronization with the heartbeat. So that maybe some of these symptoms, the loss of the self-continuity in anxiety disorders, or in the bodily awareness, the extremely strong or strong anxiety fear in these patients, might be related to an abnormal coupling between brain and heart, the respective networks. So there is indeed solid evidence for it, and we are currently conducting a larger study on that. So here you can see that the relationship between these networks and the heartbeat, abnormal coupling maybe, and that is related to psychological symptoms. So meaning there might be a desynchronization or misalignment with lack of mutual coordination between the temporal course of neuronal and cardiac activities. So then, and that ultimately, you have a lack of alignment that might also alter your temporal desynchronization, that you cannot synchronize anymore in these networks between brain and heart. And then if your heartbeat is no longer automatically integrated into your neuronal activity in an unconscious way, of course you might become very anxious. You become consciously aware of your heartbeat because it's desynchronized, and then of course you get anxious. It's the same way when you lose the coordination with your partner during the tango, you get afraid and anxious that you might lose it completely, become desynchronized not only from your partner but also from the music, and you become desperate and so on and so on. Same here with brain and heart. I'm sure you're much better tango dancers than me. And then you develop chest pain, you become more aware, heartbeat racing in the presence of normal heartbeat function. So interestingly, now this is from the psychological side, because this was about for anxiety disorders. Now you come from the other side, that cardiac patients with atrial fibrillation, that's what we're currently testing, that they have misalignment between brain and heart, and then a desynchronization. And I show you a couple of data here on that before I conclude my talk. Here, remember, I showed you the exact timing between brain and heart with this heartbeat-evoked potential. And you can see here, this is an atrial fibrillation patient who has no acute symptoms. Somewhat, they have a normal heartbeat-evoked potential, which is not exactly similar. Here you see, for instance, here it's much higher than here. And you also see some differences here in the topographical maps, the distribution of the heart-brain coupling over the different electrodes. You can see that here. And the differences become even more pronounced that when you have a rhythm disorder in your heart, you assume that it's very difficult for your brain to synchronize, to couple. Let's say if your partner dances a tango in a very irregular way, you have real problems of coordinating and synchronizing. And that's exactly. So when your heart beats very irregular, your brain has real problems of synchronizing with the heart. And that's what we could indeed observe here, what we call the intertrial coherence. Remember the phase locking, the locking to the onset of the heartbeat in the brain. And that's what you could see here. There's much here, that's the healthy control, much stronger activity here around the onset of the R wave. You have much stronger activity in the healthy subject than in the subject with atrial fibrillation, the rhythm disorder of the heart. Yeah, that's basically, I come to an end. I'm sure that some of your patients would be perfectly suitable where you have no explanation for their heart, unspecific heart symptoms, might be probably perfect suitable candidates for this kind of investigations, and would be very interesting. And I can clearly say that probably some of your psychosomatic patients who have strong heartbeat palpitations, pain, etc., and anxiety, that they show probably a similar picture like this, meaning less synchronization of their neuronal activity with the heartbeat. And then, of course, I don't need to tell you that this could eventually also lead to new therapeutic interferences, like you could try to synchronize your neuronal activities with the heartbeat by, for instance, playing external music in the rhythm of your heartbeat, and try to force your brain to synchronize within the rhythm of the heartbeat. Or you could also do maybe some transcranial magnetic stimulation in a rhythmic way and try to synchronize your brain into the rhythm of your heartbeat. So these are, if you know the mechanisms, you might also be able to develop and deliver novel forms of treatment to your psychosomatic patients. And with that, I come to the end of my talk. So it's the brain-heart coupling can probably unlock the mechanisms of psychic somatic symptoms in both psychiatric disorders or psychosomatic disorder and cardiac conditions like atrial fibrillation. And here, some of these sort of temporal spatial mechanism I discuss also in this book, which has also been, with a lot of case histories, has also been translated very recently into Italian. Thank you very much, and happy heart-brain coupling.